All right, welcome. Today, we're going to do something really cool. We're not just solving any old physics problem. We're cracking a classic from one of the most legendary problem books ever written, i.e., Irodov's Problems in General Physics. And our goal isn't just to get the answer, but to really understand the method, the how and the why behind the solution.
Now, if you've spent any time with physics, you know the name Irodov. This book is famous for its incredibly challenging but super elegant problems. Honestly, solving one of these is kind of a rite of passage. So think of this as a fun intellectual puzzle that we get to solve together.
So here it is, our case file for today, Problem 1.3. It's a story about a car's journey, broken down into 3 parts. Our mission, should we choose to accept it, is to figure out just how long that middle part, the uniform motion, actually lasts. First things first, let's break down the evidence.
You know, any good investigation starts with organizing the facts. So, our very first step is to comb through the problem statement and pull out all of our clues, everything we know for sure, and the one big mystery we need to solve.
Okay, so here's what we've got. The acceleration, which is the same as the deceleration, is 5 meters per second squared. The total trip time, tau, is 25 seconds. And the average velocity is 72 kilometers per hour. But hang on, here's the really crucial part, the first step that can trip people up. See that conversion? Since everything else is in meters and seconds, we have to convert that 72 kilometers per hour into 20 meters per second. It seems like a tiny detail, but trust me, getting this right is everything. And of course, our mystery is the time the car moves uniformly.
All right, to crack this case, every detective needs their toolkit. For a problem about motion, what physicists call kinematics, our toolkit is just a set of really fundamental equations that tell us how things move. Let's do a quick refresher on the tools we'll need.
First up, a concept that seems simple but is super powerful, average velocity. It's just the total distance you traveled divided by the total time it took. This is a huge clue for us, and we are absolutely going to use this formula to find a key piece of the puzzle.
And here they are, the real workhorses of kinematics, the constant acceleration formulas. These guys describe the relationship between all the important stuff: distance, velocity, time, acceleration. We'll be using these to figure out what's happening in the first and third parts of the car's trip. Okay, toolkit is ready. Let's do this.
Okay, this is it. We've got our clues, we've got our toolkit. Now for the fun part, putting all the pieces together, building our case, and finally cracking this motion mystery. We need a game plan. A systematic approach is always the way to go. So first, we'll clearly define the 3 parts of the car's motion. Second, we'll build 2 main equations from that, one for the total time and one for the total distance. And finally, we'll solve those 2 equations together to find our unknown. Let's get started with step 1, time.
Okay, let's build our first equation, the one for total time. The problem tells us the whole trip takes tau, or 25 seconds. Well, that total time is just the sum of the time spent doing each thing. The acceleration time, let's call it t sub a, plus the uniform time, t sub u, plus the deceleration time, t sub d. Makes sense, right?
Okay, now this is a key insight. It's one of those beautiful little symmetries you find in physics problems. Think about it. The car starts from a standstill, speeds up at a rate w, and then it slows down at that exact same rate to get back to a standstill. So what does that mean? It means the time it takes to speed up has to be the exact same as the time it takes to slow down. So t sub a equals t sub d. And that lets us simplify our time equation to tau equals 2 times t sub a plus t sub u. Much cleaner.
All right, next up, let's figure out the total distance. And this is where that average velocity clue from earlier becomes so powerful. We can just rearrange that definition from our toolkit. Total distance is just the average velocity times the total time. We plug in our numbers, 20 meters per second times 25 seconds, and bam, we get a total distance of 500 meters.
So now we're going to build another way to describe that same 500 meters. The total distance has to be the distance from the acceleration part, plus the distance from the uniform part, plus the distance from the deceleration part. Using our kinematic toolkit, that's 1/2 wt sub a squared, plus the car's max velocity times t sub u, plus 1/2 wt sub d squared. Now, because of that symmetry we found, the acceleration and deceleration distances are the same. And the max velocity? That's just the acceleration w times the time it was accelerating, t sub a. We can substitute that in and simplify the whole thing down to this nice expression. Total distance is w times t sub a squared plus w times t sub a times t sub u.
And there you have it, our 2 key equations. One describes the total time, the other describes the total distance.
Now here's a pro tip, something Irodov himself would tell you. Always solve in general form first, using the variables, before you even think about plugging in numbers. It's just a more powerful way to work. It shows you the real relationship between the physics, and you can spot mistakes way easier.
So after a little bit of algebraic magic, basically substituting one equation into the other to get rid of that t sub a variable, we land on this beauty. This one elegant formula tells us exactly what we're looking for. The uniform time, t sub u, is equal to the square root of tau squared minus 4 times the total distance, all divided by the acceleration w. Now we're ready for the grand finale.
Okay, the heavy lifting with the algebra is over. We've built our case, we've derived the master formula. Now it's time to take the clues we gathered way back at the beginning, plug them in, and get our final answer.
So let's plug in the numbers. Tau is 25, so tau squared is 625. The total distance was 500 meters, and w was 5. So that second term is 4 times 500, which is 2,000, divided by 5, which is 400. So we're left with the square root of 625 minus 400. That's the square root of 225.
And the square root of 225 is 15. So the car moves uniformly for 15 seconds. Case closed. Or is it? You know, a good scientist, just like a good detective, never just takes an answer at face value. We have to follow Irodov's advice and stop to ask the most critical question of all. Is this result actually plausible? Does it make sense in the real world?
So let's do a quick sanity check. We calculated the uniform motion time to be 15 seconds. The total time for the whole trip was 25 seconds. Well, our answer is a positive number, and it's less than the total time, which it has to be, right? That makes perfect physical sense. The verdict stands. It's plausible.
So what's the big takeaway here? It's not just the number 15, it's this powerful, reusable method. First, you deconstruct the problem into clues. Then you strategize and pick your tools, the right physics equations. You assemble your case by building those equations step by step. You solve it generally, with variables first. And finally, you always verify that your answer makes sense.
And look, this detective's method isn't just for this one problem. It works for countless challenges in physics, and honestly in a lot of other fields too. It turns a big, scary problem into a series of small, manageable steps. So my challenge to you is this. Take this method, find your own tough problem to crack, and see what you can figure out. What case will you crack next?